Hello, everyone. This is the lecture video for section 14.3. We're going to be talking about partial derivatives. Okay, so we want to develop this idea of the derivative for our multivariable functions. We've seen in Calc 1 already what derivative is, but we want to extend this idea to functions of this form, where we have f from Rn to R. Okay. So let's first kind of quickly review the idea of derivative for what we're used to, and then we'll kind of talk about where the difficulties are with these derivatives for multivariable functions. Okay, so looking at a function from a function of a single variable, something like this, like what we're used to from Calc 1 and 2, what is the derivative? Okay, we had this f prime of x, right? And that f prime of x, it's a function, and if we plug in specific values, like if I plug in a to that function, it would give me the slope of the tangent line, the line tangent to our original curve f at that point a. Okay, and I can plug in different values and get slopes, the slopes of tangent lines at different points along my curve f. Okay, so really f prime of x is giving us these slopes of tangent lines, right? Analytically, thinking of it in terms of pure math and numbers and all that, the derivative f prime of x is the limit of f of x plus h minus f of x divided by h. Okay, why is that? Remember that, okay, what is f of x plus h minus f of x over h? It's like, okay, if I have some point, let's say I have some points, let's call it x. Well, let's put it right here. Okay. What is f of x plus h minus f of x? Well, that's like 2 y values, right? So if I had, let's say I moved to the right by just h to x plus h. Okay. Well, this point would be x, f of x, and this point would be x plus h, f of x plus h. And then this fraction here, what is that? It's rise over run, basically, right? It's our movement downwards divided by, or our movement vertically divided by our movement horizontally. So that would give me the slope of this line connecting these 2 points, right? Oops. Okay. And the idea is that if I take the limit as that h gets smaller and these points get closer and closer together, so if I took a point here, okay, then that slope of the line connecting those 2 points is getting closer and closer to the slope of my tangent line, right? So if the points were really close together, okay, that's basically the tangent line. And I keep taking that limit as the points get closer and closer, and I end up with my, the slope of my actual tangent line. So that's why it's a limit. Now remember, one important thing is this limit has to be the same from both directions, meaning if my x to the h's, x plus h's are to the right of my x, and I take that limit going closer to x, okay, that's going to give me one limit. And then if I take the limit of like x minus h going to x, maybe that gives me another limit. And the derivative only exists if those 2 limits agree, if those 2 limits give me the same value. Okay, so we have similar to in section 14.2 where we had the idea of direction for limits. Okay, that's carrying over for derivatives. Okay, so in the single variable case, it's pretty easy. Our limits either approaching from the right or left, or some combination thereof. So it's pretty straightforward, right? So really, if you think of the kind of axis where we're approaching along, okay, there's really only one axis to approach along, right? I'm approaching, from this way or from this way, or I'm kind of hopping back and forth as I'm approaching. But either way, I can only approach along that x-axis, okay, for my input values. Now let's consider, all right, so now that we've kind of refreshed ourselves on derivatives for single variable functions, let's talk about derivatives for multivariable functions. And let's look at R2, f from R2 to R for a second. Let's focus on this very basic case that is going to be what we're looking at for most of the semester. Now, let's assume that this green surface is the graph of my function f from R2 to R, okay? And let's pick a point. Let's pick this, about this yellow point here, okay? That's right along this kind of ridge. We can kind of picture this if you can kind of tell what's going on here. I've kind of drawn a surface and it's kind of got like a kind of a hump in the middle, it's kind of like a mountain. And so along this ridge, we have this point here, okay? So what is that point? Well, maybe it's the point that is mapped from this point in the XY plane. So maybe this point down here in the horizontal plane is AB0, and then this point up here would be what? AB, and then f of AB. Right? Okay. I'll just write ABF. All right. Now, don't worry about the coordinates too much. Think about just the tangent lines. Okay. Think about the tangent lines to this yellow point here on our graph. Think about all the tangent lines. And if you try and draw a couple, or if I try and draw a couple, we'll see that there's actually an infinite number of them, right? Like I could have a tangent curve that's a tangent line that's just barely touching the curve going this way. Maybe one that's kind of going up this ridge like that, going this way, etc. So there's actually an infinite number of tangent lines pointing in all different not every possible direction, but in an infinite number of directions. Okay, and if that doesn't make sense, you might be asking, okay, well, no, it seems like there should only be one tangent line. Think about, picture, if you want a kind of real world example. And I thought of a kind of silly example earlier today. Imagine you're playing a video game, all right? And I've encountered this a lot in my very nerdy life. You're playing some sort of open world video game where your character can run around and climb up mountains and cross streams and all that. Okay, so let's assume you're playing one of these games, and a lot of times in these games you want to like get over a mountain or something, right? So maybe your character is, kind of, let's say this is our mountain. Let's say my character is kind of down here, and I want to kind of get over to this other side of the mountain. All right. And a lot of times in these games, if you try and walk your character up the steepest direction, right, of the mountain, you can't get up. All right. And that steepness, how steep that is, we could think of that as being like the slope of a tangent line, right? Okay, so the tangent line, maybe I'm at this point and we have a tangent line that's going directly up the steepest direction possible, right? But then what my strategy usually is in these situations is you don't try and walk straight up, you kind of try and walk at an angle, right? And you're still going upwards, but you're not going directly upwards. And usually, maybe sometimes your character can't handle going straight up, but they can handle going, kind of off at an angle. So this is another tangent line, right? I'm starting at the same point, and I have this vertical direction that's really steep, and then I have, some other directions that are not quite as steep. And I can think of all of those as slopes of tangent lines. That steepness is my slope, right? How steep it is, okay? So maybe it seems a bit more intuitive now that, yeah, we can have a bunch of different slopes at that same point, okay? Now, which ones, there's an infinite number of these tangent lines, I've said. Which ones do we care about? Do we need to consider every single infinite number of tangent lines, or do we only care about a couple? And then once we figure out which ones we're concerned with, how do we actually compute them? Okay, so these are kind of the big questions right now, standing out so far. So which ones do we care about? Which directions do we care about? Well, I'm gonna restrict myself to tangent lines for now. In this section, I'm gonna restrict myself to tangents in the direction of x and the direction of y. So if I'm back at this yellow point on my curve, okay, there's only one tangent line that points in the that you could think of as parallel to the x-axis, right? And maybe it's slope, maybe it's slope goes like this, maybe it's kind of downwards, or maybe it's kind of upwards like that. But as this line continues, it's running in some sense parallel to the x-axis, meaning let's say the y-coordinate of this point is, let's say this is at the point 4, 2, 6. Okay, my tangent line, I have a tangent line that's kind of running parallel to the x-axis. That y-coordinate is never going to change. You can think of that. What I'm trying to say is this tangent line is it exists inside the plane of y equals 2. Okay, and it's never going to go out of that plane. All right, so that's what I mean by tangents in the direction of x, tangent lines in the direction of x. And I'm also going to be concerned with tangents in the direction of y. So like a tangent line maybe something like this. That's in some sense parallel to the y-axis. Okay, so this would be the line, and it's in this plane. What we said, this x-coordinate's 4. Okay, so this would be it's a tangent line, and it's in this plane x equals 4. That's running parallel to the y-axis. Okay. And you might see the pattern here that we're going to be concerned with tangents in the direction of our independent variables, right? This green thing we said was a function of x and y. Okay, so really I'm going to be mostly concerned with tangents in the direction of my independent variables, which in this case are x and y. Okay. And how to think about that, maybe that's still a little unclear. So I want to do one more little, I lost piece. Okay, there we go. Pause here. Okay, so let's kind of go back to this example of me having this little yellow point here that I want to compute the some derivatives at that point. What do I mean by derivatives? So I'm going to be concerned with derivatives in the direction of x. Okay, and we're going to get more rigorous with our terminology here in a couple minutes. But just think of it, we're just doing kind of an intuitive thing right now. So if I remember, I'm kind of thinking of like, okay, I'm taking like a plane, my derivative might look like this. And how we arrive at that is like, maybe that this is that yellow point is at the coordinates, what we say, 4, 2, 6 or something like that. Let's let's take this plane that goes through this point along parallel to the x-axis. So the plane y equals 2. Let's take this plane. So let's take this and think about taking this plane and kind of laying it flat on our page. That's going to give us a slice of our function, right? So in this plane, this I could think of my curve as having, my surface has this curve in that plane. Okay, so it's like I'm taking a slice out of my surface. Okay, and maybe I lay it flat on my page. Okay, and it would look something like this, right? Okay, so this is that slice. This slice taken out of my curve. Okay, so let's label our axes. Okay, so what would my axes be? Okay, it's the plane y equals 2. So my plane goes, it goes across, it goes parallel to the x-axis, and then it goes up, okay, along the z-axis. So really we don't have to be too conscientious, but let's label these axes x and z. And if we really want to be if we want to really kind of keep it straight in our heads, well, this left side is the positive x side, right? And this right side is the negative x side, and then positive z, negative z. So we could keep that straight in our heads as well if we want. Don't worry about this too much. I'm just doing this to be pedantic, I guess. So we have the important thing is that we have this, we've kind of taken this slice out of our function and we've laid it flat down on the page. And now what do we have? We have a two-dimensional plane, and then we have this curve, which we could think of as a function in this plane. So really, this, we started with f rn to r, and then we've taken a slice out of this. Actually, we started with f2, r2 to r. Then we've taken a slice, and basically what we have now is we have kind of a graph of a one-dimensional function, right? And so for this graph, this graph has derivatives in the sense I'm used to. Okay, so if I wanted to consider a derivative, at this point x, I would form it in my normal way, and I can think of it in my normal way. It's like that slope of that tangent line, right? And there's only one of those. There's only one unique tangent line in this slice. Okay, and that is constructed. How is that constructed? Okay, it's that limit again. Okay, this is this tangent line. Let's say I have a bunch of points like x minus h, and then I'm making that h smaller and smaller. Okay, when x minus h is over here, okay, maybe I get this line, and then I get another one that's like this, and another one that's like this, and I take that limit, and eventually, as I take the limit of h going to 0, I end up at my tangent line. Okay. And that's going to be how we formally define these limits. Okay, everything I've done so far is just kind of intuition, right? We're thinking of the derivative in that in that x direction as like we're kind of taking a slice out of our object and laying it flat down, and then we're just finding this normal derivative. But once we do that, we might see how we define this formally. So let's go now to a formal definition. Okay. Once we confine ourselves to this slice, we can form that derivative as normal, meaning, for functions of this form that we're used to. So what we're doing, okay, remember that everywhere in this plane, we're working in the plane y equals 2 for our example, right? But the point is, in this plane, y is constant. Okay, So y doesn't change. So this limit I'm considering, and remember what this curve is, this is a slice of fxy, right? So really this limit I'm considering, and even before we talk about limits, when I do these lines that are approximations to my tangent, okay, what are the slopes of those? Let's say I'm at, let's do x plus h. Okay. Let's say I'm over here at x plus h, all right? And I want to find the slope of this line. Okay, what is that slope? It's f of x plus h. And then this is still, even though it looks kind of, you know, like a function of one variable, this is still my function from R2 to R. So this is a function of x and y. What is the y coordinate? In this case, it's y equals 2. All right, okay. And then I subtract, what do I subtract? F of x, and then y equals 2. Okay, and then to find the tangent, I divide by what? I divide by h. Okay, so that's my approximation to the tangent line. And then I take that limit as h goes to 0. And this is exactly the definition of my derivative in that slice, okay? And let's be a little bit more rigorous now. We call this the partial derivative of f with respect to y, okay? Or excuse me, partial derivative of f with respect to x, okay? So what we do is we pick a y value. I wouldn't say we pick a y value, but we hold y constant, okay, which is what we've done here, right? We said y was always equal to 2 in this plane, okay? In general, you know, this works for all our y values. So let's just say we're holding y constant, okay? And then what's changing? We're adding h to x. We have f of x plus hy minus f of xy over h, okay? And we take that limit. And this is a derivative in that slice, right? Okay. We call that the partial derivative of f with respect to x. Okay. We say with respect to x because we're taking that derivative. What's changing is x, right? We're holding y constant and x is changing. So this is like we're taking the derivative in the x direction. Okay. So we say partial derivative of f with respect to x. Okay, so that's what it's called verbally. And then the notation we have for that is f sub x, or we could also use this, okay? And a little bit, this is like a cursive df over cursive dx, okay? When we do, and that notation is important, okay? I think it's, let's see, I think it's like, there's a name for it. I think it's a dough. Yeah. So it's a symbol. It's not really a Greek symbol, I guess. But this is dou x, dou f over dou x. The terminology is not important. I usually say, it's also common to say partial of f, just partial of f with respect to x. Okay, that's how you would say this. But it's kind of this like cursive d, as opposed to a derivative of a function of a single variable. You know, we would write that with just standard lowercase d. Okay. So when you see something like this, that means derivative, you know, my function f is just a function of a single variable. When you see this stylized d, that means our function, we're talking about partial derivatives and our function is a multivariable function. So that's just notation. As I said, these are the same thing, df, dx. And what you'll probably all be writing f sub x for this type of thing. It's so much easier, and that's perfectly acceptable. So again, this is the partial derivative of f with respect to x. Okay, so that's the theory of it. How do we do this in practice? And what's happening here is what's key here in our idea is that we're pretending y is a constant and then just differentiating as normal. That's, in my rambling explanation, that's kind of what I was saying, right? Where we have this slice, y is constant, and now that we have this slice, I'm just differentiating as normal. Okay, and with respect to x. So that's what we do in practice. Okay. Let's say I have this multivariable function here, okay, and I want to find the partial derivative of f with respect to x. Okay. Again, what does that mean? Let's say my function has, this kind of graph. The partial derivative of f with respect to x, that's going to be the slopes of my tangent lines in the x directions. Okay, so maybe my tangent lines look like this, and then, as I come this way, they start curving down, something like that. But all these, oh, I've kind of skewed them, maybe like I shouldn't. Okay, and all of these are kind of in these planes that are parallel to the x-axis. Right. So you could think of it as the slope of your, if you're playing that video game and your character is kind of facing this way towards the mountain, kind of looking along that x-axis or in that negative x direction, directly in that direction, then your partial derivative is going to be the slope of the mountain where you're standing, kind of looking in this direction. Sorry. So how do we do this in practice? Oh, and I've skipped some stuff. Okay. So let's say I have this multivariable function, and I want to find the partial of f with respect to x, and we just talked about what that means. It's that slope of that mountain in front of us when we're looking in the x direction. I hold y constant, and I differentiate with respect to x normally. Okay. So in this equation, let's pretend y is a constant, okay, and differentiate each of these terms. Well, I have x cubed plus ln of y, and I'm assuming y is a constant, so I can think of this whole thing as just a constant, okay? So when you have x cubed times a constant, what's the derivative? 3x squared times that constant, ln of y. And I'm in the wrong place. I should be, no, I guess I'm in the right place. All right, good. All right, so I differentiate this term, I get 3x squared ln of y. Let's move on to the second term. Okay, I want to differentiate this, and again, I'm treating y like a constant. So if y is a constant, okay, well, derivative of e to the power x is just e to the x. Okay, so I just have this. And then if y is a constant, sine of y is a constant, right? So I don't have any x's here. What's the derivative of a constant? It's just 0. Right? So that's a 0. Okay, so this is my partial derivative of f with respect to x. 3x squared ln of y plus e to the power x over y. Okay, so it's fairly, there's no new differentiation techniques as far as like the mechanics go. It's just holding y constant and differentiating with respect to x normally. Okay, so that gives us our partial derivative of f with respect to x. Now, as you might have guessed, everything works the same for the y direction, except I hold x constant. Okay, and that's going to be the punchline. Okay. So again, I have this surface, and I'm considering the derivatives in the y direction, partial derivatives in respect with respect to y. Meaning, okay, I'm looking at all these points on my surface, and the tangent lines, I'm considering tangent lines that run parallel to my y-axis. Okay. So they live in these planes like this. And again, if I'll lay those planes flat on the page, let's say I take this plane and lay it flat on my page. Okay, and let's see. I would have the y positive direction, z positive. Okay, and then my curve, my slice of my curve would look something like that, right? I'm just kind of guesstimating. Okay, and then once I'm confined to this kind of slice, the derivative I can calculate just normally. So let's say I'm looking for I'm considering the approximations. Let's say I want to find the derivative at this point y. Okay. What are my approximations to my derivative? My secant lines, they're called. Okay. So if I go to y plus h, okay, I have this point y f x y, right? Because this is the curve f x y. And then here, and remember in this slice, x is constant. Call it x is, well, we'll just leave it as x. Remember, x is constant in this plane. All right, and then what's this point? Y plus h, f of x, y plus h. Okay. And then what's the slope of that secant line? It would be f of x, y plus h, minus f of x, y over h. And I take the limit of those slopes as h goes to 0, okay? And that's going to give me my partial derivative with respect to y, okay? And the notation, again, fairly straightforward. F sub y, same thing as dou f over dou y, or partial of f over partial y. Okay? And that's our partial derivative of f with respect to y. And then let's see another, well, I guess we have the same exact function, right, as last time. Okay. So let's compute the partial of f with respect to y now. Okay. So now I'm holding x constant, and I'm differentiating with respect to y. Okay. So what's the derivative of that first term? Well, if x is constant, x cubed is constant. So I just have x cubed times 1 over y, because 1 over y is the derivative of ln of y. Okay. Then I have what? Ex is constant, so I just pretend that's a constant number. I differentiate 1 over y, and I get what? Negative e to the power x over y squared, right? And now at this this term, all right, derivative of sine of y, that's cosine of y. So this is my derivative of f with respect to y, my partial derivative of f with respect to y. All right, so we've seen how it works in the x and y direction. And in fact, okay, well, if our function is only two variables, okay, we're going to mostly be concerned with just those x and y directions, okay? Everything else, there's no other independent variables, so I don't have any other nice derivatives. We'll talk about directional derivatives later, but what I'm trying to say is if I have a function of many variables like f, x, y, and z, I can find partials for every independent variable. So in this case, I'll have the partial with respect to x. Let's write it as f of x. I'll have partial with respect to x, I'll have partials with respect to y, and I'll have partials with respect to z. Okay, if they exist. And the method is the exact same. When I'm computing partial with respect to z, I basically treat x and y both like they're constants, and then I differentiate with respect to z normally. Okay, so really straightforward. Now, just a word of warning. Just like with functions of a single variable, right? Not all functions are differentiable, right? So if you remember, the classic example is the absolute value function, absolute value of x. This function is not differentiable at that point, at that sharp turn, okay? Remember, differentiability is kind of somehow related to how smooth a curve is, right? If it's got these jagged angles, it's not going to be differentiable at those points. So derivatives are not guaranteed to exist. We often take it for granted that they exist, but they don't always. And just like with this single variable case, absolute value of x, these multivariable functions are not guaranteed to have derivatives either. We're going to mostly be working with functions that are differentiable, but we could have kind of an analog to the absolute value function. Imagine I had kind of a shape that was kind of like this, and it kind of sloped down and then hit the y-axis and then curved back up. Okay, so it kind of formed a sharp V there. Well, it's not going to be differentiable if I tried to differentiate in the x direction, right? What are those slices going to look like if I take slices parallel to the x-axis, kind of lay them flat on the page? Well, that curve is just going to look like that absolute value function again, right? That slice. So we would expect it's not going to be differentiable at that point there. That's just a little side note. A little word of warning. For the notation, there's a lot of different forms of notation for the partial derivatives. A lot of different texts use a lot of different forms of notation, and they're all the same, and they all mean the same thing. So here are several of those. I've only done the different notation for partial of f with respect to x. Okay, so we've already seen the f of x, right? And that's the same as fx parentheses xy. That just means, okay, this is a function. This is still a multivariable function, and you're still plugging x and y into it. And then we saw this notation, partial of f over partial x. And again, this is the same thing. These two are similar to, recall, for functions of a single variable, we could have written this df over dx, or we could have said d dx of f, right? Same thing. Similar concept at work here. If your function f x y, if you're saying z is your function of like equal to your function x squared plus y, blah 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 blah. You have your function on this side, and you're saying, okay, it's equal to z. Well, instead of having partial f over partial x, you could have partial z over partial x. This f1 here, f sub 1, that's the same thing as this. It's just, okay, you have a function f, and it's got inputs, and what you're saying is you're differentiating with respect to the first input, whatever that is. usually you'll label it x or whatever, but there's no reason we have to use x as the letter of our input. So f1 is just kind of a way of saying, hey, we're differentiating with respect to the first input. If I was taking the derivative with respect to the second input, I would say, if I was differentiating with respect to the second input, I would say maybe f2, f sub 2. Similar thing at work here. The big capital D is just saying, okay, you're differentiating, and the 1 says you're differentiating with respect to the first component. This is the same thing. You're just saying you're differentiating with respect to x in particular. Okay. So which ones do we need to know? I would not worry about the bottom line so much, really. These up here, and really these two are pretty much the same, and these two are pretty much the same. Okay, if you're going to use something in this class, I would kind of stick to these two here in the middle. That's sort of the most straightforward. You won't. This is really more kind of operator notation. You're probably not going to see that in your careers. So let's do a couple examples. Just finding the derivatives. So let's say this is my function of x and y, fxy equals sine of x over 1 plus y. Let's find f sub x and f sub y. Okay, let's find f sub x first. Okay. Well, I'm going to just treat this like a function of x and pretend y is a constant. Okay. So this is a chain rule type situation, right? I got a function within a function. All right, so imagine you just had sine of x over a, and you wanted to differentiate that using chain rule. That would be sine of x over a times the derivative of what's inside, which is just 1 over a. You'll bring that out front. Okay, same process at work here. I'm differentiating this with respect to x. I'm treating y like a constant. So my derivative should be what? Cosine of x over 1 plus y times the derivative of this stuff. So times 1 over 1 plus y. Okay. How about fy, f sub y? Again, it's basically chain rule. I'm differentiating with respect to y, treating x as a constant now. Oh, 1 plus y. All right, so I differentiate the sine to get cosine, and then I need to multiply by the derivative of what's in here. Well, if I'm differentiating with respect to y, what is the derivative of this? That stuff inside I could basically write as x 1 plus y to the negative 1. Differentiating this, okay, with respect to y, negative x 1 plus y to the negative 2, right? Oh, and that's when I put it in the denominator, it's just positive 2. Okay, so that should be my derivative with respect to y, my partial derivative of f with respect to y. All right, moving on. Oh, here's a good, this is another example just straight from the textbook. We can also use partial derivatives in conjunction with implicit differentiation. Okay, if you remember implicit differentiation from Calc 1. Let's assume z is a function of x and y, but we don't know exactly what that function is, right? The form of f is unknown. Okay, the exact form of f is unknown. I would still like to be able to find the derivative. I would still want to be able to find the partial derivatives of f. So in particular, I want to be able to find or z, however you want prefer to think about it. I want to be able to find partial of z with respect to x. Now, if I don't know f, that can be a little tricky. Okay, but I have this equation here. I have this equation that kind of relates my z to my x and y's. Okay. So how would we find dz dx? Okay. I'm going to differentiate this equation with respect to x. Okay. Now, at first, it starts out pretty easily. I'm taking the partial derivative of this whole equation with respect to x. Okay. So what is the first term? Okay. X cubed becomes 3x squared. Okay. If I'm differentiating y cubed with respect to x, well, I'm treating y like a constant. That just becomes 0. Now, here's where things get a little tricky. I want to differentiate z with respect to x. And remember, I'm assuming z is equal to f of xy. All right. Well, I don't know exactly what that is, but if this is true, right? If this situation is true, if I have this z is equal to this equation, okay, then this is basically chain rule, right? I have f of xy, that because that's my z, right? And I had that cubed. Okay. So by chain rule, this should be 3 f of xy, which is z, 3z squared, times the derivative of what's inside. So dz dx. Okay. And then I continue on. Okay, what's the derivative of this thing? I got 6xyz. With respect to x, well, let's see, that would be like product rule, right? Because I have x here, and I'm assuming z is a function of x. So let's see, it would be 6yz plus 6xy dz dx. Okay. Equals, what's the derivative of 1 with respect to x? 0. And then I can drop these parentheses here. All right, and then I have, let's see, let's collect all our dz's, our dz dx's. Let's get all those together. And let's take them to the other side of my equal sign. So I have 3x squared plus 6yz equals negative 3z squared dz dx partial z partial x minus 6xy dz dx. Okay. And then let's factor out those that partial z partial x. Okay. Last step, I want to get dz dx by itself. So I'm going to divide both sides by this term in parentheses here. And I should end up with that. And that is correct. I just need to factor out the 3. I can factor out 3 from everything. So that's what? Do it on this side. X squared plus 2y squared over negative z squared minus 2xy. I can factor out the negative. I can bring the negative sign out front and turn this into a plus. And is that what the book has? Y squared plus 2xz. Oh, I was getting scared for a second. I was looking at the wrong line. Negative x squared plus 2yz, yep, over z squared plus 2xy. Yep, perfect. Boom. And I'll let you guys try implicit differentiation with respect to the y variable and see if you come up with the solution, which is in the example 3 in the textbook. Once we can do partial derivatives, we can also talk about higher order derivatives, meaning, okay, for a function of a single variable, okay, r to r, remember we had first derivative, we had second derivative, third derivative, and so on. These when we have more than one derivative, when we take the derivative more than once, those are the higher order derivatives. Okay, so just let's kind of build up quickly from the functions of a single variable. So remember that the second derivative of a function f is basically the derivative of the first derivative. Okay, so if I want to find the second derivative of f, well, first I find the first derivative, right, df dx, and then I differentiate that, and that gives me, you know, this notation here, d squared f over dx squared, which is just the notation for the second derivative. Okay. And we can do the same thing with partial derivatives. So let's say I want to find partial of f, or the second derivative of f with respect to x, which we would kind of write in notation like this. Okay. So d squared dou squared f over dou squared dou x squared. Okay. How would I find that? Well, first I would find the partial of f with respect to x, and then I differentiate, take the partial derivative of that with respect to x again. And that's going to give me that dou squared f over dou x squared, which I could also write f sub xx, meaning I've taken the partial with respect to x, and then I've taken the partial with respect to x again. Now, the interesting thing about these multivariable stuff is, like in the single variable case, when I take the second derivative, you know, there's only one choice for what I'm differentiating in terms of, right? Like if I have a function of t and I take the second derivative, okay, it's just there's no choice but to differentiate with respect to t both times. Now, for multivariable, that's not the case. Okay, what if I take the partial with respect to y of the partial with respect to x? Okay, what does that give us? So what I'm saying is take the partial with respect to y of the partial with respect to x. Okay, and this all makes sense because remember, this is going to be, you know, I'm starting with a function f of xy. I'm taking its partial derivative. That's going to give me this thing in here, which is still a multivariable function. You know, I could still think of this as a df, a function df dx of xy. Okay, still a function of two variables. And if it's still differentiable, well, I can now take the derivative of this thing with respect to y, which is what this notation here is denoted. Okay. So this partial of derivative with respect to y of partial of f with respect to x, well, that becomes this notation. Dou squared f over dou x dou y. Okay, and the order here is important. This is saying, okay, I'm differentiating f twice, and I'm differentiating with respect to x and then with respect to y, which gives me this, f sub xy. Again, order being, okay, I'm doing derivative with respect to x first and then y. Is the order thing important? Okay, I'd say yes. Now, by the end of this section, you might not think so, but rest assured that order of partial derivatives does matter, okay? You can't just take it for granted, all right? What I mean is, does the f sub xy, is that the same thing as sub yx? Okay, the answer is not always. Okay, and this is an important distinction. Okay, I would be doing you a disservice if I let you go forward thinking that this is always true. It's not always true. However, it's it's pretty much always true in this course. Okay, in fact, I don't think it is always going to be true in this course, and it will probably always be true for the rest of your undergraduate courses, but and honestly, it's been mostly true in my grad school. But there have definitely been cases where it was not. This is a very important theorem. It's not something you can always take for granted. Okay, so just remember that this equality is not always true. However, we do have some nice conditions under which it will be true. Okay. So under these certain conditions, and these conditions are fairly common, this equality will hold. This will be true in most cases. I think that'd be a good test question, though. I would ask true or false. The mixed partials are always equivalent. Okay, these things are called mixed partials, by the way. When I have like fx and like derivative of f with respect to x and y, I've got, it's not just x by itself. That's called a mixed partial derivative. Okay, so I think that'd be a good quiz question, test question. All right. So when are these things equal? Well, we have this nice theorem. I assume that's pronounced Clairaut. I'm not 100% sure. Let's say it's Clairaut. Clairaut's theorem. Okay, so suppose f is defined on a disk D that contains the point AB. Okay, this is very common setup for problems or theorems in mathematics. Something defined on the disk. What does that mean? Well, it just means that we have the point AB, and then the area we're working in is, it contains this, kind of nice neighborhood of AB. Okay, so we don't have any kind of weird examples where we have our point AB on the boundary of something. Okay, that boundaries are always hard to work with, so we're just saying AB is inside some nice interior. Where was I? Suppose f is defined on a disk D that contains the point AB. If f sub xy and f sub yx are both continuous on D, then f sub xy at AB is equal to f sub yx of AB. So remember these partial derivatives. Okay, this is a partial derivative. It's second order partial derivative. It's d squared f over d, what do we say, dx dy. Okay, this is still, remember, this is still a multivariable function. So we can ask, is it continuous? Okay, just like with any other function. Okay, and we can ask the same question for, okay, this. All right, are they continuous? And if the answer to both of these is yes, then these two things are going to be equal. Okay, and the proof of that is fairly complex. I had to do it once upon a time back in my early days of grad school, but don't worry about the reasoning behind this. Just remember that this condition holds. Like if these second order partials are continuous, okay, then the mixed partials are going to be equal to each other. All right. I haven't written anything else. Let's see. Do I need to talk about anything else though? Okay. Functions of more than two variables. I talked about that. It was, I kind of integrated that into my whole lecture, so I don't think anything needs to be said there. Higher derivatives, we just talked about, Clairaut's theorem. Partial differential equations, okay. You're not going to have to solve any, but we could at least talk about partial differential equations real quick. The other day, about a week ago, I guess, in our lecture together, I mentioned differential equations. Okay, so for those of you who are interested, I'll just give like a couple more minutes explanation of differential equations and partial differential equations. Okay. So differential equations. They kind of come in two flavors. There's ordinary differential equations. Also, this is commonly just called differential equations or diff-EQs or ODEs, okay? So that's one branch, and then there's partial differential equations. Okay, so that's another branch. And you see this word partial here, and we've been talking about partial derivatives, and that's not a coincidence. So let's talk about ODEs real quick. ODEs, it's a way to, it's this branch of mathematics that's concerned about finding a function based on information about its derivatives. So let's say I'm given an ODE, an ordinary differential equation that looks like this. And this isn't how you would I'm going to kind of rephrase it so it's in a format you would understand, you might be familiar with. Okay, let's say I'm told that f prime plus f is equal to 0. And I'm not told exactly what f is. And now I'm just working with a function of a single variable, by the way. I'm just working with a function of a single variable. And I'm told this equation is always true for this function, this particular function f. But they don't tell me what the function f is. I use ODEs would be the kind of branch of mathematics that is concerned with discovering what the exact form of f is. Okay. So if you were just told this, what do you think f is? Okay. Well, its derivative and the function and its derivative have to cancel out. Okay, and maybe if you are especially clever, or maybe if you've seen some materials from ODEs before, you might think to try a function like e to the negative x. Okay, does that work? Well, let's plug it in and see. If I plug this into my equation, does that equation hold true? Well, this f would be e to the negative x, and then what's f prime? F prime would be negative e to the negative x. Okay, and yeah, that is true. Okay, so e to the negative x is one solution to my differential equation. Okay, so that's kind of what ODEs is. And so differential equations, what does the name mean? It means we have these equations that involve derivatives of an unknown function. Okay, so when we're talking about ordinary differential equations, it's very our familiar idea of derivatives. It's derivatives of a single variable function. Now that we've defined partial derivatives, we can talk about what partial differential equations is. It's the same concept. I have an equation, I'm given some equation that involves derivatives of a function, but now I'm assuming my function could be a multivariable function, and my equation could involve partial derivatives. So maybe I'm told f of x, f sub xx plus f sub yy equals 0. And, I'd solve this equation for f. And don't ask me to solve any partial differential equations. Partial differential equations is much more difficult than ordinary differential equations. For those of you who are getting, in that STEM heavy track where you have to take calc 1, 2, 3, differential equations, etc. The differential equations you guys all have to take is just ODEs, okay? So it's the more simple branch, and not to say it's easy or anything. I mean, I think it does have a reputation of being somewhat easy, but that's only at the basic level. It gets incredibly complex the higher you go, obviously. But in general, this PDEs is you could say it's a more difficult branch, I guess, but that's kind of not doing justice to the term. But that is what PDEs is. It's differential equations in with partial derivatives. Okay. All right. So that's my rant about the different branches of math, and I will leave you guys to do the problems and the homework, and we can talk about the difficult stuff next week.